In this video, we're going to review sort of where we got to in class last Thursday, and then we're going to look at one simple theorem, and then we're going to stop there for this video. But this is just part one, so there'll be other videos out there. I do this for a couple of reasons. One, the video size is more manageable; it's easier to upload to the cloud, and also it's easier to sort of manage that way. Okay, so if you recall from last time, we did talk about orthogonality. So if we have two subspaces, in this case I'm calling them U and V. And so if those are two subspaces of Rn, so in this section we're pretty much in Rn. And so those subspaces are orthogonal if basically, if the transpose, if the product, the dot product, so if U transpose times V is equal to 0, if that dot product is equal to 0, and that's true for every U in fancy U, or big U there, and every little v in fancy V. So in other words, if you can take any vector out of U and do the dot product of it with any vector in V, and you'll always get 0, then those two spaces are orthogonal. And the way we notate that is using the perpendicular symbol. Okay, so again, we talked about that before. And then we also defined what do we mean by the orthogonal complement of a space. And so that's this U with a subscript, a superscript of the perpendicular symbol. And so this consists of all elements in Rn x, such that that x is orthogonal to every vector in U. And I highlighted this part because I may not have written this on the board last time, I can't remember. But we do want that condition there to be x transpose y equals 0. For each, like I wrote it here, each y in U. So again, a vector is an element of the orthogonal complement of U if its dot product with every vector in U is 0. And so a simple example, I think we put this on the board too, is that the span of E1, the orthogonal complement of that, is equal to the span of E2 and E3. And I also mentioned that, you may remember from vector calculus, you may be more comfortable with E1 as the I vector, E2 is J, and E3 is K. If we're talking about R3 as illustrated in my picture here. So again, so you can think about the vector space, the span of E1, that's really just the x-axis in essence. And so any vector that's on the x-axis, parallel to the x-axis, would be orthogonal to any vector in the yz plane. And in essence, the yz plane is the span of E2 and E3. Okay, so that's just a review of sort of where we made it to last time. So now let's do this one little theorem. So one part of this theorem is to actually show that the orthogonal complement actually is a vector space. It's always a vector space. So notice in my example, we know that it's a vector space because it's equal to the span of E2 and E3. And we know that the span of vectors does give us a vector space. All right, so let U and V still be subspaces of Rn, just like we're working with now. So the first thing we're going to show is that if the subspaces are orthogonal, then they only intersect at the 0 vector. So the only thing in their intersection And let me try to do that a little better. There. So the only vector in the intersection is the 0 vector. And then secondly, the orthogonal complement of U is in fact a subspace of Rn. We're not going to prove both parts here. We're just going to prove the first part. For the second part, you just use the subspace test. So we're just going to do the proof of the first part. Okay, so let's pick an arbitrary vector from the intersection of the two. And what we want to show is, even though we've chosen a vector arbitrarily from this intersection, we're going to show that that has to be the 0 vector. Okay, so because U and V are orthogonal, or perpendicular if you want to say it that way, well, let's think about it. That tells us that every vector in U has a dot product with any vector in V that must give us 0. Well, W, by definition, W is an element of U, and it is also an element of V. So because we arbitrarily picked this vector out of the intersection of those two, then the dot product of W with itself must be 0. Well, remember that the dot product of a vector with itself gives its length squared. And this has got to be 0 by the definition of what W is. But if the norm squared of a vector is 0, then, or the length squared of the vector is 0, then the length of the vector is 0. And we can actually put equivalence there. And, well, if the length of a vector is 0, that's equivalent to saying that W is 0. Okay, so therefore, we picked an arbitrary vector out of the intersection of U and V and demonstrated that, well, that has to be the 0 vector. So therefore, the intersection consists only of the 0 vector as desired. Okay, and so that's the proof of 1. And again, let me just make a remark here. The proof of 2, use subspace test. And so that would be a good problem to practice. See if you can get through that subspace test. Okay, so this is the end of the first video. This will be part 1, so stay tuned for the additional videos. In this video, we're going to look at a theorem, and we're going to prove that theorem. And then we're going to draw a picture of the 4 fundamental subspaces of Rn. So again, remember that in this section, when we're talking about orthogonality, we're primarily in Rn. All right, so the row space, which is fancy Ra, and the null space, so fancy Na, of, well, we need to talk about what is A. We know A is a matrix, and it's M by N. And what we want to prove is that those two spaces are orthogonal. So just have a little color here. I'll switch to orange. Okay, so let's see if we can prove these two facts. And let me also emphasize here that, technically the row space is I think we wrote it as R superscript 1 by n, but, the technical differences between these spaces kind of blur. In essence, R to the 1 by n is the same as Rn. So normally when we talk about the row space and the null space, we're not so interested in the fact that we're talking about rows. Typically we think of all those, a row vector, a column vector, or just, an n tuple. All three of those are considered to be parts of Rn most of the time. Okay, so just to point that out again. So to start, let's let U be an element of the row space. Well, so that, if U is an element of the row space, then U is equal to some combination of the rows of A. And since A is m by n, we know that there are m rows. And also remember that the way we distinguish between the rows vectors and the column vectors is that when we refer to row vectors, we put an arrow over the top, and that's just the convention of this textbook. So U is equal to sum C1 times A1, row A1, plus C2 times row A2, and plus sum Cm times the last row of A. So this is for some constants, or you could say use the word coefficients there, Ci. Okay. So now let's pick a vector. Since it's from the null space, let's call it n. So here n is a vector. And this is from the null space of A. Instead of ending the sentence there, let's say so that A times n is the zero vector. Well, if A times n is equal to 0, then it would be clear that the dot product of any row vector of A with n has to be 0 as well. Okay, so let's write that down. It's clear that AI, so if we take any row of A and do the dot product with n, and that's equal to 0. Notice, a lot of times when I do the dot product, I put the transpose there on the A, but the A is already known to be a row vector, so that's why I'm leaving that off. Because typically we have a column vector by default, and then we transpose it to get a row out of it. All right, so it's clear that this is equal to 0. This is for each, whoops. Let's go back to this color. For each I equals 1, 2, up till m. Whoops. M. So for every row vector AI. Well, from this, it's pretty easy to get where we're headed, because now if we do the dot product of U, which notice that U also is already a row vector, because it's a combination of the rows of A. So the dot product of U with n is, it's C1 times A1 plus C2 times A2 plus all the way to Cm times Am. And it's the dot product of that with the vector n. And then using properties of the dot product, we can write this as the sum. Basically, we're just going to distribute. So we can write this as the sum of C I times AI's dotted with n. And that says I goes from 1 to m. Okay. And that's equal to the sum as I goes from 1 to m, and we could pull the CI out. Wait, can we do that? No, I'm sorry, we can't do that. Because that's not that constant changes all the time. But the key here is that this part is always the zero vector from before. So we'll call that star. So this part is a zero vector from star. And so this is basically the sum of a bunch of constants times the zero vector, which is the zero vector. And that's it. So we can say as desired. Because what did we do? We chose an arbitrary vector u from the row space, and we picked an arbitrary vector n from the null space, and demonstrated that the dot product of those two must be 0, and 0 is a scalar, not a vector. So let me fix that. And also here, because the dot product of those two is just the number 0. So again, the dot product is just a scalar, just a real number. So anyway, we've shown that the dot product of anything from the row space with anything from the null space is 0, which is what we wanted to show. Okay, and one thing to note is that, this theorem applies equally well to A transpose. So, well, we've kind of got 4 spaces going on here. So let's talk about the 4 spaces. And I'm going to do a new piece of digital paper to illustrate this. So what we're looking at are the 4 fundamental spaces. And I'm going to try my best to give you a nice picture here. Okay, so think of, I found it helpful to think of the linear transformation. So remember that we can define the transformation from Rn into Rm as, T of some vector x is equal to our matrix A times the vector x. Okay, so our x's come from Rn, and our inputs, if you want to think of it that way, and the outputs are in Rm. And so and this diagram is due to Dr. Gilbert Strang from MIT, who is a very good lecturer in linear algebra. If you ever get a chance to watch his videos on MIT OpenCourseWare, I would recommend that you do that. Okay, so anyway, so this is sort of the picture I got from his textbook and his lectures. So this represents the row space. And then to kind of pictorially show that we have orthogonality here, so there's the null space of A. And that's basically what our theorem just told us, right? The row space and the null space are orthogonal. And just to emphasize that, both of these spaces, in essence, come from Rn. But just because we've got a diagram showing that these two spaces are orthogonal, just let me emphasize that there's also other stuff. So there are also others in Rn that are not represented here. So these two spaces don't partition. Well, they wouldn't partition anyway because they do have the zero vector in common. But my point is that there are other vectors besides those in the row space and the null space. Okay, so if we pick a vector in the row space, then it maps to, so maybe this is our x, then it's going to map to all the AX's, and that lands us in the column space of A. So remember that the column space is a set of all these AX's. So it's the image. The column space is the image of this transformation. It's the image of T. And so even we have the zero vector there. And remember that any x that we choose from the null space is going to go to the zero, which is zero is that little corner there. And so we can also talk about over here in Rm, there's the null space of A transpose. And so if you think about it, except for, if we totally disregard the fact that some of these are columns and some of these are rows, then the column space of A, let's think about this. I want to say that that's the row space of A transpose. Think about that. I'm not saying that it is, but I believe it is. So this is something to think about. Okay, so, and also let me emphasize that even though we know that the column space, we know that the row space of A transpose, which we believe to be the same as the column space, the row space of A transpose is orthogonal to the null space of A transpose, but then there are also other vectors in Rm that are, that don't fall in either one of those two subspaces. Okay, so that's sort of a diagram of the four fundamental spaces at play here. And again, I think it is really helpful to look at them in terms of a linear transformation. Okay, so that's it for now, but there will be another video, so stay tuned. In this video, we're going to talk a little bit more about this idea of the four fundamental spaces. And so one thing that I did want to point out is, in the last video, I asked the question for us to think about, is the column space of A, equal to the row space of A transpose? And we can erase that question mark because it is true. Well, I guess I'll leave the question mark so all this makes sense. But so it is true, and it's an easy equivalence actually because, well, first of all, we know that any A times X is an element of the column space. That's easily true. Well, then by taking the transpose of AX, that implies, right, so we're doing the transpose of AX, and that's equal to this, and that's known to be an element of the row space of A transpose because it's a row vector times the matrix A transpose, which all that does is gives us a combination of the row vectors of A transpose. And then also the equivalence easily goes the other way because it is always true that a product, it is always true that a product such as this, some vector, some row vector times A transpose, that's always going to be an element of the row space of A transpose, and then you can just do the transpose the other way, and you'll get the AX back, and that's in the column space of A. So that's That's an easily true. That's an easy equivalence. Okay, so those two are the same. Okay, and so in the next theorem we're going to look at, it's what the book calls the fundamental subspaces theorem. We're going to prove that the null space of A, so we're back over here on the left side over here. We're going to prove that the null space of A is in fact equal to the orthogonal complement of the row space of A. So, the idea is that, so here's the row space of A, and the orthogonal complement, maybe it's bigger than the row space of A. So we've already proven that the row space of A and the null space of A are orthogonal. So we can pretty well say that at least we know that the null space of A is a subset of the orthogonal complement of the row space. But we're going to show that in fact they're equal, and there's basically nothing else in the orthogonal complement of the row space except what we have from the null space of A. And that's what the book calls the fundamental subspaces theorem. And so I've got a start to it right here. This is theorem 5.2.1 in the textbook. Well, I'm looking at a slightly older edition. I'm looking at the 8th edition. So, but they're pretty close. So, the theorem that I'm talking about, it has the title fundamental subspaces theorem, and I would be willing to bet that it's the same in the current edition. But I do want to make a caution here. The textbook uses the R notation, R of A, not the way we do. When I do R of A, I'm talking about the row space of A. But the textbook uses R, that capital R, as the range of the linear transformation L. The one we defined earlier. L of X is equal to the matrix A times X. So keep that in mind if you look at the textbook. So I think the textbook would, if you see R of A, that's actually the column space of A, not the row space of A in the textbook. Okay, but when we're going to stick to our notation. So when we write R of A, we're talking about the row space of A. Okay, so let's see if we can do this proof here. So again, what we're trying to show is that, in essence, we just need to prove number 1. So if we can prove number 1, then number 2 will be true automatically, because A transpose is a matrix just like A is. So in essence, all we have to prove is part 1. So we can just make a note here. 2 follows from 1. So really all we have to prove is part 1. Okay, so we've already seen that the null space of A and the row space of A are orthogonal. So, or we could say thus, the null space of A is certainly a subset of the orthogonal complement of the row space. Because remember that the orthogonal complement of the row space is the set of all vectors in Rn that are orthogonal to every vector in the row space. And we've already seen that the null space, anything in the null space satisfies that criteria. So we've got a subset relationship. But now we want to show that in fact there is equality here. So now we need to show that the subset works the other way. So let's pick some arbitrary vector x from the orthogonal complement of the row space. This means that if we take any, if we take any row vector of A and we take the dot product with x, so just to emphasize that these are both vectors, we're going to get 0, right? Because x being in the orthogonal complement of the row space means that the dot product of any row of A with x gives 0. And hence, we see that A, the whole matrix A times the vector x, must give the 0 vector, which implies that x is an element of the null space of A. And that's pretty much it. So thus, oh, have I said thus yet? Yeah, okay, well. How about ergo? There's one I don't use much. Ergo, well, we chose this x arbitrarily from the orthogonal complement of the row space, and we showed that x is an element of the null space, so that shows that the row space, the orthogonal complement of the row space, is a subset of the null space, and therefore they are in fact equal. And we're done. Because like I said at the beginning, if we can show that 1 is true, then 2 is true as well, because A transpose is a matrix in its own right, and its null space is equal to the orthogonal complement of its row space. Okay, so let's stop here for this video, and then in the next video I'll pick up with an example of this theorem. In this video, we're going to look at an example of the fundamental subspaces theorem. So that's the one we just proved earlier. So we're going to demonstrate that the row space of this matrix is perpendicular to the null space, which we know that's true from the theorem, but let's just see that in action with this example. Well, I think if you just think about it for a second, it's pretty obvious that the row space of this matrix is just the span of the vector, the row vector 1, 0. And because in order to get the second row, you just multiply that vector by 2. So let's see, what is the, so what about the null space of A? So what about that one? So we need all vectors little x1, little x2. So all vectors in R2 such that this product, so our A times this vector x is equal to 0. Well, let's say I think we're going to need for this to be true, we're going to need little x1 to be 0, and then little x1 and little x2 can be any real number. You can do, like we normally do. You can actually solve the system by looking at the augmented version, but and I think it's going to be easily seen that this will just give us a whole row of zeros at the bottom, and so we'll essentially just have the first row survives, and so the x2 is our free variable and x1 is our pivot variable. So that's that's the sort of method that we can use, the formal method that we've used to see that. But this one was kind of easy to just, kind of eyeball it and tell. So the null space, so just to explicitly write this down, the null space is the span of, let's see, it'd be like 0, 1. Yeah, the span of the column vector 0, 1. Because x1 needs to be fixed at 0, and then x2 can be any real number. And so I think it's clear to see any element from the row space. So let's see. So an arbitrary element from the row space would be like alpha. We'll just use alpha times that vector 1, 0. And then sort of an arbitrary element from the null space would be something like 0 times some number, 0 in the first position, and then beta in the second position there. So it's just some beta times that vector, that 0, 1 vector. And well, it's easy to see that the dot product there is 0. So that's sort of a simple example exercising that fundamental subspaces theorem. Okay, so let's look at a theorem in the book. We won't prove this, but just to record it. In the book that I'm looking at, again, which is an earlier edition, it's the 8th edition, it says this is theorem 5.2.2. So if S is a subspace of Rn, then, and this is something you probably have kind of suspected, or it certainly will make sense to you, I think. The dimension of S plus the dimension of its orthogonal complement is n. And I think that's pretty clear from, well, that was pretty clear in our simple example before. We were looking at R3, and I gave you the example of the span of E1, and the orthogonal complement of that is the span of E2 and E3, essentially. And so it's clear that the first one was a one-dimensional space, and the other one, the span of E2 and E3, that's a two-dimensional space. And so you add the two together, and you get 3. Okay, excuse me. All right, so furthermore, essentially this next part says that if we have basis vectors for S and basis vectors for the orthogonal complement, then we can put them together, and that'll be a basis for Rn. So x1, x2 until maybe xr, if this is a basis for S, and then xr plus 1, xr plus 2 until xrn, until xn, is a basis for the orthogonal complement of S, then, like I said before, just put them together. So x1 and x2 until xn, that is a basis for all of Rn. And again, we won't prove that, but I think that's kind of it's sort of an obvious result, I think. Okay, so we'll stop this video there, and in the next video we'll talk about orthogonal matrices and look at some of the properties satisfied by such matrices. Okay, so in this video we're going to talk about orthogonal matrices and some of their properties. But before we get there, we need a definition, just a couple of definitions. So we're going to start here. So a set of vectors, and you can see here I'm calling them V1, V2 until Vn. And explicitly we're talking about a subset of Rn. So pretty much in this chapter we're just focusing on vectors in Rn. So that set V is called orthogonal if the dot product of any two distinct vectors from that set is equal to 0. So in other words, if I is different from j, then that ensures us that we're dealing with two different vectors. Because if you're doing the dot product of a vector with itself, that always gives its length squared. Okay, so if in addition each one of these vectors, so if each vi has length 1, then we call this an orthonormal set. So the normal, I think the idea is the vectors are normalized, right? So each one of them has been shortened down to a length of 1. And that's essentially what the property that we're after and what defines an orthogonal matrix. Okay, so let's get a definition of that. So a matrix, and by convention, people typically use Q for orthogonal matrices, so we're going to stick with that. So a matrix Q which is n by n, is called orthogonal. Whoops. Well, this thing is just not cooperating with me. There we go. It's called orthogonal if its column vectors are orthonormal, or form an orthonormal set. And this is one term that I sort of wish wasn't done this way, but it's kind of weird to me that we call a matrix orthogonal even if we require that the column vectors have unit length 1. So not only do we require that any two columns of A be orthogonal, to each other, we also require that each column is a unit vector. Okay, so we have to have both of those things be true in order to have an orthogonal matrix. And so let's do a theorem here. And so we're just going to let Q be an orthogonal matrix. One property that's pretty interesting here is that the inverse of an orthogonal matrix is its transpose. And so that's the first property. And then the second property is that if we multiply a vector by an orthogonal matrix, then the result will have the same length. So in other words, if we think about a linear transformation as like if we think about L of x equal to some Q x, where Q is orthogonal, then this linear transformation, I mean, it may redirect its input vector, but it won't change the length of it. So just to write that down, so the norm, or the length of this q times a vector x is the same as the length of the vector x. And this is for any x in Rn. Okay, so let me erase this part. Just kind of was using that for illustration. Okay, so let's see, why is this true? And well, I guess I'll move this down to the next part, or to the next page. Let me cut that instead of copying. Okay. So for one, and I'm just going to kind of sketch the idea of the proof here, but we'll hit all the major parts. So if we multiply Q transpose times Q, then, well, let's think about what that is. So, well, remember that the matrix Q, there's a Q1, a Q2, until Qn. And so if we compute this product of Q transpose times Q, well, if we're in an off diagonal position, like say row 1, column 2, so like what goes here, then let me say, this is not really, I'm not going to be really rigorous here, so this is a proof idea. So if we look at not the first but the second column there, and we, ask ourselves, well, what goes there? Well, wouldn't it be Q1 transpose times Q2? Because it's we're looking at the first row of Q transpose and the second column of Q. So I believe it would be Q1 transpose times Q2. Well, since this is an orthogonal matrix, then that dot product is 0, isn't it? I mean, that's sort of that's how we defined it. So any off diagonal entry, well, you'll just get a bunch of zeros. And so what if we're looking at the dot product, one of the values along the diagonal, like, for example, what goes in the first row and the first column? Well, that's pretty obviously going to be Q1 transpose times Q1. But we know that is its length squared, and each one of these has length 1, so it's just 1. So sure enough, we'll have a bunch of 1s down the diagonal. And so that's, the multiplication one way to get the identity. And then, of course, if you just take the transpose of both sides, so take the transpose of the left side, and then the transpose of the identity matrix is, of course, just the identity. Oh, well, that's going to give us, if we do the transpose, that's not going to help us too much. Well, that way I think we could do something like this. So let me go back to the other color. Let's let the matrix A be Q times Q transpose. Then A times Q would be Q times Q transpose times Q. And that's equal to, well, let me just stick with this. So if we group together the Q transpose times Q, well, we've already shown that that's the identity. So this is equal to Q, because that, again, that I've grouped together is the identity. So that tells me that A, whoops. So this implies that A is the identity matrix. Let's see, is that true? Well, the last recording cut off on me while I was looking into that, but we do have essentially the proof complete, because we're trying to show that Q times Q transpose is the identity. Well, we know from our work on determinants that that the determinant of the product, which is the determinant of Q times the determinant of Q transpose, this cannot be 0. And so each one of those matrices has to be non-singular. Q is non-singular and Q transpose is non-singular. So it is invertible, and the inverse is what it is. So that essentially completes part 1 there. All right, so the second thing that we want to see is that the length of QX is the same as the length of X. Well, let's look at the length squared of QX, the length of QX squared. Well, we know that that is QX transpose times QX, which is X transpose Q transpose times QX. But Q transpose times Q is the identity. So essentially this is X transpose X, which is the norm, or the length of X squared. And that essentially establishes that second property. Okay, let's look at a simple example of an orthogonal matrix and kind of exercise these properties here. So this is an example from the book. So for any fixed theta, if we look at Q being, I think we've looked at this matrix before. So the first column is cosine theta, sine theta. And then we have negative sine theta, cosine theta. Well, if you look at the columns there and remember your trigonometry, I think you can be convinced that this is an orthogonal matrix. Well, let's see. Definitely the normal part. So let's just check. So first, what would be the dot product of the twos? Well, let's just pick. So this first column is Q1, and the second column is Q2. So we really only have one dot product to check. But let's say Q1 transpose times Q2. That would be cosine theta, sine theta as a row vector, times negative sine theta, cosine theta. And it's pretty simple to see that that's 0. And then, so what's the second thing we have to check? Well, remember that with an orthogonal matrix, to ensure that this is an orthogonal matrix, we also have to verify that each column has unit length. Well, and that essentially follows, so it follows that each, so that norm the length of Q1 is equal to the length of Q2 is equal to 1. And that pretty much follows, well, let me see. I didn't really write that correctly. Let's do it this way. This is true. This follows from the basic Pythagorean identity, right? Sine squared theta plus cosine squared theta is equal to 1. Okay, so there's a simple example of an orthogonal matrix. And let's see, what would this matrix do to the vector? Well, I'm not going to do that. I was going to say, let's just pick a vector and like 1, 1, and then multiply this matrix by 1, 1, and then compare the length of the result. But I think that'd get a little nasty. Maybe I can come up with a simpler orthogonal matrix to work with. Well, let's do this one for the case where theta is 45 degrees. So how about we do, I'll just stick with red. So let's let Q be, let's see, it would be 1 over square root of 2, 1 over square root of 2, and then negative 1 over square root of 2, and 1 over the square root of 2. So this is essentially that first example where theta is 45 degrees. So what would this do to the vector 1, 1? Let's see, what would that give us? Well, let's see, I think that first component is going to be 0, right? Yeah, because we'd have 1 over the square root of 2 times 1 plus negative 1 over the square root of 2 times 1, which is 0. And then the second component would be 2 over the square root of 2. Is that right? Yeah, 2 over the square root of 2, which is the square root of 2. And then, okay, assuming I did that product correctly, let's compare the lengths of these two. So the length of that input vector is, square root of 2. And then the length of this one is clearly the same. So there's an example where we've sort of verified that multiplication by this orthogonal matrix will preserve the lengths for us. And so we'll just stop there for now.